Alright, we have a nuclear fusion problem. So basically the way this is going to work is we're going to take the total energy is going to be the number of reactions times the energy per reaction, and then we're going to use the total mass is equal to the number of reactions times the mass of the atom. Okay, these are both just counting equations. They're not on your formula sheet because they're just kind of intuitive. Alright, now we have the total energy here. We can get that from the fact that the world uses energy at a rate of 15 terawatts, right, for 1 year, or for 1 day. So we're going to multiply that power times 1 day. We're going to find the energy of the reaction by using delta mc squared. We're going to find the total mass because we know the mass of the atom is boron 11, right? 11 AMU. And so what we're going to do, first we're going to find this first. That's going to be step 1. And then we're going to set it equal to this. That's going to be step 2. That's going to find us the number of reactions. And then step 3 is going to be plugging the number of reactions in here and solving for the total mass. Okay? So you should work ahead and see if you can do what I do. Alright, so we're going to start by finding delta M. Delta M is input minus output. So the input, we got a proton plus boron 11, so 11.009306, and then we're going to subtract carbon 12, right? That's 0.016582 AMU. Now if I multiply that by our conversion factor, 931.5 MeV per mu c squared, right, times c squared, right, E equals delta mc squared, I get an energy of 15.45 MeV. Now again, if you wanted to, we could convert this into kilograms and multiply by c squared and get joules, right? This is 2.47 times 10 to the minus 12 joules. So if I wanted to use MKS units, what I would do is I would say, well, the energy is equal to 0.016582 atomic mass units, and I'm going to convert that into kilograms. And then I would multiply by c squared. Right? So if I work this out, I get this. Okay, so that's the first step. I've calculated the energy in a reaction. It's this little bit. It's 10 to the minus 12 joules. Now I'm going to calculate the total energy. Okay, total energy is power times time. So it's 15 times 10 to the 12th watts times 1 day. And then I'm going to multiply that by 24 hours in a day. And multiply that by 3,600 seconds in an hour. And that gives me 1.3 times 10 to the 18th joules. 1.30 if you really want to be precise about it. Okay, so now I can calculate the number of reactions, right? That's the total energy divided by the energy per reaction. So that's 1.30 times 10 to the 18th joules. That's how much energy is used in a day, and I'm going to divide by this little bit of energy per reaction to get N, which is 5.2 times 10 to the 29th atoms. Now, how much boron is that? Well, the total mass is that number, 5.2. Right, we're using this equation up here now. 5.2 times 10 to the 29 atoms times 11 AMU. And I don't really need to use all the significant figures here. I'm just using 2 or 3 sig figs. And then I convert that to kilograms. And I get 9,600 kilograms. Right, so about 22,000 pounds or something like that of boron is needed in a day. Which sounds like a lot, but remember, we're powering the entire world for 1 day. So that's actually not bad compared with how much coal we use in a day or any other fossil fuel.